everything. But what if that's not true? What if our cosmos actually has a reverse twin that exists beyond the Big Bang, and we are therefore living in a mirror universe? Well then, we would have arrived at the core of an exciting theory that seems extremely outlandish at first, but which, in the second instance, is actually suitable for answering some of the biggest open questions in cosmology. It may seem, according to our current understanding, the Big Bang marked the beginning of literally that the Big Bang theory is untouchable. After all, according to our established assumptions, the cosmos unfolded from a tiny starting point about 13.88 billion years ago, where time, space, and matter emerged together from an original singularity. But despite all the outstanding significance, we must not forget that the Big Bang is still overshadowed by gigantic question marks. The corresponding theory explains neither what could have triggered the Big Bang in the first place, nor why matter and radiation are so inexplicably evenly distributed, and why matter dominates over antimatter. And so it happens that these days, experts are increasingly approaching the much-cited Big Bang from a slightly different direction. Given the great unsolved mysteries, could it really be that there was simply nothing before the Big Bang? Or are we ultimately not dealing with the beginning of everything after all, but merely with a cosmic transition? Well, a certain Stephen Hawking took a very clear position on this and stated that time itself only began with the Big Bang, which is why the question of what was before that makes about as much sense as asking what is actually south of the South Pole. In other words, Hawking was convinced that there could have been nothing at all before the Big Bang. But other experts have their problems with precisely this assumption, because in addition to the questions about what came before and what triggered it, the almost ridiculously even distribution of matter and radiation in our universe also presents us with a huge mystery. Because no matter which direction we look in or what distance we look at on a large scale, there are comparable densities and distributions of galaxies, nebulae, and radiation everywhere. In this regard, scientists generally refer to the theory of cosmic inflation, in which the original universe expanded by a factor of 1,030 to 101,000 in a fraction of a second. And yet the question of whether cosmic inflation really occurred is sometimes just as controversial as the question of whether countless parallel universes must not also have been created in the process. Was the Big Bang, in fact, a big bounce? But let's assume that our universe really doesn't include the big picture, that another, earlier cosmos already existed before it. What does it actually mean in concrete terms? Well, it may come as a surprise, but in fact, the idea of such a cyclic universe is anything but new, and even Einstein thought this picture was quite plausible. From Einstein's general theory of relativity, the Russian mathematician Alexander Friedman, in turn, deduced that the expansion of the cosmos can also be reversed. In plain language, this means nothing more than that the universe would contract to a certain point and then expand its radius to a certain point before shrinking again, and so on forever. Accordingly, the universe would thus be subject to a continuous cycle of expansion and contraction. In other words, a continuous cycle of birth and demise. And indeed, this hypothesis also offers some decisive advantages, because if the cosmos really has an eternal cyclical character, we would no longer be confronted with the problem of the initial singularity. The question of how all matter could arise out of literally nothing becomes obsolete in this context, because it has always existed in some form. There never was anything like an absolute nothing. And this theory could also explain the confusing homogeneity, because where the Big Bang is followed by a big bounce, the phase of contraction ensures that everything is made uniform, so to speak, and as soon as the renewed expansion occurs, this uniformity is maintained. And even the question of the previously unknown trigger for the Big Bang now has an answer, because the cause of every new beginning is simply the end of the previous cycle. So far, so promising, if it weren't for the problem of entropy. According to the second law of thermodynamics, the degree of disorder in a closed system continues to increase, and that also applies to the universe. As a result of the ever-new cycles, entropy would therefore have to increase forever. This means that with each cosmic restart, a little more radiation is created in relation to matter, and that the cosmos will eventually reach a state of maximum entropy in which neither atoms nor stars or galaxies can exist. But that's not all. Because of the entropy problem, more and more disordered particles would be squeezed together with each contraction of the universe, while the following new beginning would be accompanied by a stronger dispersal. Conversely, this means nothing other than that each new cycle would always last a little longer than the previous one. In terms of the past, however, this would also mean that the cycles are getting shorter and shorter the further back you look. And just as with the Big Bang Theory, we would also arrive at some point at a starting point where everything is concentrated. But in the same breath, and this is the exciting thing, experts have now found ways and means to solve the entropy problem. According to loop quantum gravity, the fabric of spacetime is not continuous, but structured into tiny indivisible units known as loops. When connected, the loops form the basic structure of the universe, with the particles representing the nodes of the net-like construct. In this way, we can imagine the universe as a single shimmering of constantly changing tiny connections that are neither visible nor tangible to us. In this context, the original singularity of the universe cannot have existed. Loop quantum gravity only allows for finite physical values, which means that an infinite density is not permissible. In the same breath, however, the quantization then causes an event that is no less spectacular. At the point of the Big Bang, gravity is reversed. Instead of exerting an attractive force as usual, it suddenly pushes everything away. As a result, space is practically turned inside out, which in turn has some astonishing consequences. Accordingly, the loop model literally screams that the Big Bang was not the beginning of everything. In contrast to the theory of relativity, it also yields valid mathematical results before the Big Bang. So there could really be a big bounce in which a precursor universe collapses in on itself and is then pushed back into larger scales by the antigravitational effect of its own microscopic network. Conveniently, the resulting fluctuations in matter and energy density would erase all information from the previous cosmos. In other words, every new universe suffers from a severe case of amnesia, which consequently also provides a solution to the problem of entropy since this is virtually reset to zero. The universe can start over carefree. Do we live in a mirror universe? These solution models make a big bounce more likely again. But that's not all. In fact, a few years ago, physicists at the Perimeter Institute for Theoretical Physics in Canada uncovered further evidence of such a big bounce. In detail, the experts around Neil Chirok wondered what would happen if the rules of symmetry that apply to particles and forces according to the Standard Model were applied to the universe as a whole. The corresponding rules state that all interactions in particles are symmetrical with regard to charge, time, and spatial configuration and interactions. In other words, this means nothing more than that for every particle, there is a counterpart that corresponds to its mirror image. An interaction of this particle would also occur in reverse time, as if mirrored. But what would happen if this so-called Captain symmetry also applied to the entire cosmos and its development since its creation? If, consequently, not only the particles and the forces but also space-time itself could be mirrored, well, This case would be accompanied by a remarkable circumstance. For then the universe before the Big Bang and the one after it could be regarded as a pair of universe and anti-universe. The Big Bang would then not only have been the beginning of our cosmos, but also that of its mirrored counterpart. We would therefore have a kind of twin universe in which, however, the opposite signs apply and time runs backwards. As a pair, the universes would then also fulfill all the rules of Captain Symmetry, something our cosmos alone cannot do. In the same breath, the theory of mirrored universes could also crack some puzzles of the established cosmological models, such as why matter dominates antimatter in our universe. In principle, both should have been created in exactly equal parts during the Big Bang. But if there is a mirror universe, the drastic symmetry break is restored. Chirac explains, while the universe had a slight surplus of matter after the Big Bang, there was a slight surplus of antimatter in the universe before the Big Bang. Furthermore, the mirror model also manages without cosmic inflation. In principle, this should have caused turbulence in space-time, which would have left its traces in the cosmic background radiation and in the form of primordial gravitational waves. So far, however, experts have not been able to detect any such inflation relics. But if the Big Bang was, in fact, just a kind of envelope point between two mirror universes, then there would be no need for such a phase of expansion faster than the speed of light. According to Chirac, the physical processes involved in this transition would provide the corresponding explanation. But the crucial question is whether it would even be possible for us to bring this exciting theory from paper to reality and to directly prove the existence of our cosmic mirror. Well, the sobering answer is that, unfortunately, this would be impossible. And yet Chirac and his colleagues emphasize that there may at least be some verifiable evidence that could lead us on the trail of the unreachable mirror world. More specifically, the crucial detail could lie dormant in the particle world. If one of the neutrinos turns out to be massless, this would be just as much of a clue as if neutrinos turned out to be Majorana particles, particles that are their own antiparticles. Another hint from the mirrored fence would be if future searches continue to fail to bring primordial gravitational waves to light. Aside from this, however, researchers are also looking for further experimentally verifiable evidence that can specifically substantiate their theory, and it will be interesting to see how our overarching view of the universe will change as a result. And now we're looking forward to your click on the subscribe button. Feel free to press the thumbs up and subscribe now to never miss a new video from us again.